Thank you. And thank you very much for giving me the opportunity to talk a little bit about the work I've done in my PhD. So it's a joint work mostly with Alain Trouvé. Then I'm going to present another small part, which is current progress work, and it is with Ryan Molly. It's going to get a bit similar to what he presented this morning. And yes, what I've tried to do is generalize LDDMM method. So maybe first I want to review a little bit what is LDDMM and what setting I'm going to work with, because I feel like we sometimes have different formulations or different settings. So let me just give a brief review of what it is. So originally, it's just a matching problem. We're given two images, a source image and a target image, and we want to find the best diffeomorphism that deform the source image to the target one. So to do so, we can just solve this, minimization problem. So on the right, we have the data attachment term, which allows us to deal with some noise or things like that, and just measures the similarity between the deform image and the target image. And on the left, we have the distance on the diffeomorphism group that comes from a right-invariant metric. And this is because we want the diffeomorphism to be as close as possible to identity. We gain a little bit of okay, so this is one matching problem. We can already generalize this to matching other types of shapes. So let me also say a few words on Argiller's definition of shape spaces. So we're given Q a shape space. It can be possibly infinite dimensional manifolds. So you can think of images as before, or curves, surfaces, landmarks, even varifolds maybe. You're given also the group of diffeomorphism, and you'll suppose that it will act on your shape space. Now, when we'll have the right-invariant metric on the group of diffeomorphism, this will induce also a metric on the shape space. And the metric we're going to use are not Riemannian, they are actually a sub-Riemannian metric. To do so, and it's a strong sub-Riemannian metric. So we just define a Hilbert space that is embedded in the Lie algebra, and this defines by right invariance a sub-bundle of the tangent bundle. Now we only have a metric on this sub-bundle and not the total tangent bundle. So this means that when we're going to look at curves in the diffeomorphism, we will restrict to curves that have Eulerian velocity inside this space V. Now we have defined this. We can, similarly to Riemannian geometry, define a sub-Riemannian distance. So once again, we restrict to curves that has that have velocity inside the bundle we have defined. And the nice result we get is that this construction gives us a complete metric space. And as long as the distance is below infinity, we can have a minimizing curve between points. Moreover, if we add a little regularity assumption on V, we have also a global existence and uniqueness of solutions of the geodesic equation. So this is the setting we're going to work with, but we wanted to extend it to right-invariant sub-Riemannian metrics on other groups than the group of diffeomorphism. I'm thinking of on some extensions. We saw this morning with Ryan, the example of coupling rigid motions and non-rigid motion. You have also this semi-direct products that can appear when you want to do metamorphoses plus LDDMM or kind of or things like that. And I think also Barbara Gris is working on metrics, on right-invariant metrics on this semi-direct product. I also want to say a few words on this products, the direct product of a diffeomorphism group, because I promised in my abstract that I would give some multi-scale application, and also first group I was working on during my PhD. So the idea is that, yes, we want to do a multi-scale matching in a hierarchical fashion. So we want to match first at a coarse scale, and then refine and refine, and at the end match at the finite scale. So each diffeomorphism of this group will act at a different scale, okay? And we also suppose we have, let's say we have L diffeomorphisms. We suppose we have a L Hilbert space. These ones will represent the deformation at the coarse scale. This one at the finest. Okay, and what are we going to do then? We're going to generate each of our diffeomorphisms. So at scale 1, we're just going to take a velocity inside V1 and integrate this equation. And that at the final scale number 2, we're going to use again this velocity and add a little refinement. Now, we take phi2 being the same u1 plus a refinement u2 composed with phi. We do things continuing until it's phi l t is the sum of each contribution. Okay, and the metric we are going to use is just the sum of the norm of u1 plus the norm of u2 to the norm of. This is my example of multi-scale match. So yes, so here we see that we want to generalize to other groups, but we also want to stay in this banner setting. So let me introduce another tool that we're going to need, which is this notion of Half-Lie groups. Like all the groups that we are working with are not exactly Lie groups because we have only the smoothness of the right translations, and the left translation is only continuous. This is not really a problem. There is a little way to gain some regularity for the left translation. And here I'm quoting a paper from Martin Bauer, Philip Harms, and Peter Michor. And the way to think about it is that if you say that J is an equivalent of the Sobolev diffeomorphism of regularity S, then we'll introduce the family of a family of Half-Lie groups JK. And GK will represent ds plus k, which that now, when we are going to do the product between an element of JK and an element of G, this will be a CK mapping. Okay, and it's similar that that we have for the usual diffeomorphisms group. Okay. Now, as I said, we were also going to need to integrate curves in the Lie algebra into curves in the half-Lie group. We want to solve our ODE, and yeah, I'm giving you a slight extension of a result that also appears in this paper. Here I'm taking a curve that is L1 in time in the Lie algebra of J1, and we can always integrate this into an absolutely continuous curve in the space J1. Furthermore, this evolution mapping has some regularity properties. We can differentiate of same fashions as a class did. Okay, so let's introduce our sub-Riemannian setting. So once again, we're taking the Hilbert space inside the Lie algebra, and we retrieve the results of Arguellier, that we get a metrically complete space, and we can find minimizing geodesics. And moreover, if we add the same condition of regularity that B is inside the algebra of G2, we will have uniqueness and global existence solutions of the normal geodesic equation. So let me talk a little bit about the dynamic of the geodesics. I don't want to go too much into the technicalities of the different kind of geodesics for a sub-Riemannian matrix. Here I'm taking the same problem as at the beginning. We have the functional, which is the sum of the energy from our sub-Riemannian metric, and here just a data attachment term. Okay, and once we do that, we can try to find our geodesic equation. The thing is, since we are in a sub-Riemannian setting, we won't really be able to find a geodesic equation directly on the velocity. We have to go into the cotangent bundle, because the sub-Riemannian metric gives us actually a metric on the cotangent bundle. We only have a Hamiltonian formulation, which is given using simple canonical isometry between the dual of B and B. And yes, what we get is, as I said earlier, geodesic flow generated by this Hamiltonian, globally defined and unique given initial position and initial covector at 0. Now, since we're dealing with right-invariant matrix, we have a right-invariant Hamiltonian. And this means that we can also have a sub-Riemannian Euler-Poincaré or Euler-Arnold equation. Once again, we won't have an equation in the Lie algebra. We only have the equation on the dual of the Lie algebra. We only get this. This is also a good thing. Maybe I can erase this. Because we've just talked about the dynamic in the group G, but remember that we're actually dealing with a shape space Q and a smooth action of J on Q. Okay, so we can also look at the actual Hamiltonian dynamic on Q, which is given using the infinitesimal actions that I will not see. Q. So this is the Hamiltonian and the tangent bundle of Q. And what we get here is that, once again, we get a momentum And this momentum will also be a solution of the Euler-Poincaré equation. It means that once we integrate the Hamiltonian flow on Q, we can always come back to the Hamiltonian flow on J. This also means that if we describe our data using two different shape space, Q1 and Q2, but with the same metric on the space J, it means that as long as we have the same momentum, same initial momentum for Q1 and Q2, then the geodesic will actually be in J. Okay, and now I want to give little applications using this coupling of rigid and non-rigid motions. This is a part that is going to be quite similar as Jan's part. We define this semi-direct product, which is also a half-free group. And it will allow us to have rigid parts and the non-rigid parts. We also define Q as being a direct product of isometries. And here, which we erase once again. The idea is that, sorry, what? Yes, there is a rotation, translation, and diffeomorphism. And I want to do a similar thing as my multi-scale hierarchical thing. So in Q, the isometry part will just be scale 0, let's say, that gives us the orientation and position of our shape. And then a refinement, which is a scale 1, and that I represent with landmarks, so 8 points in RD. And then I will apply first the first rigid scale on this, the first scale, and then the rigid and the non-rigid on the landmarks. So when we do this, we get the following Hamiltonian. But what we can see here, so the letter P here denotes the covectors that will generate the non-rigid parts. And these covectors will also play a role through the angular momentum in the dynamic of the rotation that we will find. And to deal also with this problem, we can just use for V a space that is invariant by rotation and translation. Usually the case, like we usually take a Gaussian kernel or something like that, which is invariant by the action of rotation and translation. This means that the angular momentum and the sum of Pi will be a constant of the dynamics in the third theorem. We can just take them equal to 0 at the first time step, and then this will be constant. And if we do this, little change of variable, we get actually a separation of each contribution. Here I'm going to present a kind of the same example as Ryan showed earlier. Here I do a matching of the blue curve, the red curve, only with the translation and the LDDMM. It's a nice matching. With the black arrows represent the non-rigid part.